Hi, Srini. Hope you have a good break.
Hello.
Hello. So the next class is Wednesday lah, 3 to 4. Am I right?
Yes, Chair. I thought like cancelling today, but then since 8:30 early a bit, so okay, I can have 1 hour today.
Because 2 hours is too stressful for
Long.
you. Too long and too stressful for you. For
Too
me,
much to absorb. Yep.
it's better to have 1 hour class. Then you can refresh yourself and then refresh your memory. Okay, let's carry on. Let me just get the...
So at least you're still okay with me. I think if I go university, I don't think like I can turn like how many hours they'll have the lecture.
University is more stressful, not like your school, where you can more or less the class is more or less fixed. University you have to run from one lecture to another and
to ask and everything.
Run around and then
or ask the friends if they understand or something.
You have to work with your friend. No more tuition already because it's too specialized. So you have to be more disciplined.
I'm on my own.
Homework. They give you homework, your assignment. Usually the assignment carries some mark, probably 10% for the whole semester. And then you are given a fixed time to do it. So the trick is as soon as you can understand the topic, do it. Or talk to your friend, discuss with your friend, make good friend, and then help them, you help each other. Okay, let's go to number 5. A simple AC generator has a coil of 250 turns, that's your N. Each with area, that's your area. Remember to change it to meter square. The coil is rotated at a frequency of 5 revolutions per second. So that is basically your omega lah. In a uniform magnetic field of, that's your strength, about the axis perpendicular to the magnetic field. Calculate the peak EMF generated. Yep, what's the peak EMF generated? Haven't studied that more or less, but doesn't matter. This is using a bit of your what you have learned in your STPM, peak value. Yep. How to calculate? Can you remember? I think I given you a formula. Your peak EMF. I said I didn't teach you how to calculate your root mean square, that's all.
NBA omega.
Okay. NBA omega, good.
Just but why omega? Because the centripetal force are that one.
Just put in your formula. You cannot just go back to your initial flux formula and then differentiate it. Right? Differentiate, that's your E naught. Right? That's your peak value. You can remember it, good, use your formula. If not, as I said, go to the basic and put in your value. Right? B, that's your B. That's your, sorry. That's your B. Your A is that one there. Change it to meter, so 10 to the power minus 4. Right? It's better to remember this formula. It's quite common, they use it. They give you a cm square. And N, 250 omega, this omega per second, so it's correct unit. So it's 5, multiply out, 13.4. So this one is a bit more challenging. The part B, root mean square value of EMF generated. How do you calculate root mean square? That's your STPM work. You will study the next topic also. How to calculate the root mean square. Can? Remember, this semester you have to score all the subject very well. Next semester you have a I think your stress level will be greater already because you are repeating all your subject.
Yeah, Sem 1 and 3 together.
So it's more stressful. Semester you have to do all your subject, improve on all the subject, get as high as possible. Yep, how to calculate root mean square. Can remember? Yeah, just take your E naught divided by root 2. That's all. 13.4 divided by root 2. Instantaneous value of EMF generated when the plane of the coil is at 30 degrees with the magnetic field. Okay, how to calculate? Yep, how to calculate? Yeah, there's no, we have already done that earlier. Give me the correct formula so can remember. Yeah, if it's a plane of the coil rotating through, then he use cos, right? Or if you have to calculate the angle between the area and the field, then you have to use sine law. Then you have to take 90 degrees minus your theta law, right? Omega t is your angle. Right? Put in your value. VAN is your 9. This one 13.4 and cos 30 11.6. Can or not? It should be theta lah, not omega t. Omega t anyway is equal to theta, the angle turn through in time t. Yep, can or not, can or not, can or not. Any problem?
No problem, sir.
Okay, let's try under focus. Next Wednesday, we'll go to cell inductance. All right, let's go to focus. Structure question number 2. This one. A piece of wire XY, that's your XY, of length 2 cm. So you are supposed to neglect that, right? Assume that this is 2 cm. On a 2 cm metal track, that's your metal track, 2 cm, right? So actually it's slightly less than 2 cm, slightly longer than 2 cm. But anyway, you just imagine that the rail is very thin. With uniform field given you, an identical wire PQ, right? That's your PQ. These two can be moved, right? The rail are the one that is fixed. Enters the magnetic field with velocity of u 15. That one PQ must enter with velocity u given by 15. And remember to change to meter. Total resistance of the two wire is 0.60 ohm. The resistance of the track is negligible. What is the EMF induced in the wire PQ when it enters the magnetic field at time t equals to 0? Yep. What is the EMF induced? What formula do I use? What formula do I use? Can or not? Can or not?
Oh.
That's all. E is BLV. Right? Instead of BQV for force, you BLV. Or whatever, you memorize it. Find the induced current, PQ, and state its direction. Okay. How to calculate the induced current? Yep. What's the direction? Yeah. Right hand rule. Field is going in. Motion is to the right. So where's the direction of the current? Induced current or induced EMF? On PQ. Remember, focus on PQ. Don't focus on the real. Okay. That's your velocity. Your field is going in. That's your field going in. That one. First finger is going into the page or going to the screen. And that's your correction or current. Yep. So where's the direction of the current? Use the right hand rule. Can or not? Huh? That's how you calculate your EMF. Put in your value. There's your B. L, 2 cm. Convert it to meter. Your speed in cm, convert it to meter per second. Okay, I got this value. Your answer in the book is this value. Let me know, check and see. Let me know if I'm wrong. And use your formula, E divided by R, V divided by R. Right? In this case, it's E divided by R. Calculate your current. So it's milli, that's why we convert to meter volt. And your R is given you 0.6. You can write in milliampere or 10 to 3.4 or 10 to the power minus 3 ampere. Okay, so where's the direction of induced current? Use the right hand. Field is going in. Motion is to the right. So where's your second finger? Yeah, that's your motion. That's your field going in. That's your current. Can? Q to P. Okay now, can now, Q to P. Yes, can or not, can or not. I want me to show you.
Sure.
Can, okay. Explain why the wire PQ decelerate as it moves in the magnetic field.
No induced current, right?
Got induced current, that's why we calculate that.
No,
Right?
but in what?
It's from Q to P. Q to P.
Oh.
Oh, this getting you to apply your knowledge. Chapters, topic 16 and topic 17 together, that's all. 16 and 17 are closely related. Magnetic field. One is induced. One is force on moving conductor, that's all. Right? One is force on current carrying conductor, not moving conductor. Moving conductor is induced current. Yeah, you got a induced current in QP. It moved through the rail and it come down here, XY. Right? So these two currents are opposing each other. So if the current are opposing each other, there's a what? There's a repulsion. Right? If there's a repulsion, Q and P and X and Y, there's a repulsion. So it's moving to the right, repulsion is to the left. So it will decelerate, you know? Yeah. Currently the two wires, X, Y, and PQ are in opposite direction. Right? It's moving up, Q to P, moving across the rail, moving from X to Y. They are in opposite direction. So there's a repulsive force. Topic 16. If the current in the two moving conductor is in opposite direction, if it's charged, it attracts. If it's current, it repels. Remember that. So if there's a repulsive force, the repulsive force on PQ is to the left. So it's opposite. So that's why it decelerates. Okay or not?
Okay.
Okay, the last one. The wire XY is observed. Right? We're now focusing XY. We move PQ. Is observed to move to the right as the wire PQ approaches. Explain why. Yep. I already given you more or less the answer already. Yep. Can or not? Can or not? Yeah, the answer is there. Current, induced current move from Q to P, move along the rail, move along XY, and then goes back. So between XY, the two currents are opposite direction. So they repel each other. That's the reason why XY is moving. Okay.
Okay.
Any comment? Anything not clear?
Nope.
Okay, I just whet your appetite for next week. Then we will stop to take a short time, that's all, since we still got a little bit of time.
Wait, what?
I just go over with you a bit of cell inductance to prepare you. That's all. Right? So that next week you are ready, since we still got a bit of time. No point in wasting it. Anything that you want to ask? Any question you want me to solve for you? Yep. Got any question you want me to solve for you? Okay, if not, let's go over just to starting only. so that to get you moving, you can start and read your book. As I say, your book is quite good. Self-inductance, you still got 3 topics left. So next year, you'll probably only be able to start with self-induction. You're not going to complete it. Right? And remember your value of constant, your formula, your data sheet. Right? That's an essential one, permeability of free space. Where to find it. Okay, so all these things you must remember. Okay, how to calculate the flux or definition for flux, flux linkage, and then Lenz law, conservation of energy. What's Lenz law? What's Fleming's right-hand rule? What is Faraday's law? And then there is your Faraday's law. And then there's your how to calculate your EMF in the straight wire or straight conductor moving in the magnetic field. Cell induction. Right, what we're supposed to study, explain the phenomenon of cell induction and define. We want to define phenomenon. Phenomenon is what we observe and use a formula. So basically, we are just using this formula to define. And then use this formula and derive the equation for self-inductance for solenoid. So we get this formula for solenoid. And then after that, energy is the short topic. Okay, self-induction. What is it? Self-induction is the phenomenon in which an EMF is induced in a conductor. It can be a coil, right? We just say the conductor, anything that allows electricity to pass through. When the current in the conductor changes. So it doesn't have to be a coil. It can be a conductor moving in a field. Right? Same thing. Right? So key is phenomenon is what we observe. EMF is induced. Right? Current in the conductor changes. What is happening? When you close this switch, right? There is a switch, K is a switch. The current cannot rise instantaneously, right? Not like a resistor. It takes time for it to flow through it. So when it flows through it, what is going to happen? Right? The current starts to increasing. So the field start, the current will produce a magnetic field. So it start to increase. So when it start to increase, remember it's the field start to change across the coil. So EMF is going to induce in the coil. That's what it means by self-induction. Right? EMF is induced in the coil. Right? So we are just basically using Faraday's law. EMF is induced if there's a change in flux. Right? We call it self because it is on the coil itself. And then remember, your flux linkage is just BAN. Right? The field due to the coil times the area of the coil times the number of turns. And then your B, right, is solenoid, is mu naught, N times I. So if you want, you can put all these inside this equation. That's what we are going to do. Right? So no current, no flux linkage. If the switch is off, no current, no flux linkage. So no EMF induced. As the switch is closed, current increases. Remember, it doesn't go straight away reach the final value. Right? The current starts to increase as it starts to flow. It takes time to flow. That's the current. That's the current. It's moving through the circuit there. And then remember, the current flow in a conductor, there's going to be field around the conductor. So as the current increases, the field increases. So the field increases, that one, current increases, field increases, flux linkage also increases, right? The B increases. So flux linkage increases, it changes with time. So you have an induced EMF. EMF is induced in a solenoid. If there is an EMF, then it must produce an induced current. And that induced current opposes the direct current. That's the reason why the current takes a long time to rise up. Because there's an opposing current called the induced current. It opposes, this is a direct current, this is opposing current. And we call that induced EMF back EMF. Right? It opposes the direct EMF. That's a direct EMF provided a battery. Right? We call it back because it opposes the direct EMF. I can show it there. Back, E back. E back is for your back EMF. And this back EMF, E, is proportional to the rate of change of current. Right? As I said, we can derive using this formula and show that. Can I do experimentally, or we can show it hooking this B into here, which we are going to do next week, and then derive that equation. Right? Or we can show experimentally that equation that E back is proportional to a quantity L, a constant called self-inductance, and the rate of change of current. Negative sign is always means that the back EMF opposes the direct current, or the back EMF opposes the supply voltage. That's the supply voltage. Okay, any comment?
Not sure.
Definition of self-inductance. Okay, so that's a new quantity that we want to define. Self-induction of conductor is just, we are just using this formula. We're not worried about negative sign there. Take the di dt down. So it's your back EMF divided by the rate of change of current. That's how we define our self-induction. Memory work, right? In statement form, in formula form. I is the induced current. L is in Henry. So the inductance of conductor is 1 Henry. Back EMF is 1 volt. Rate of change of current is 1 ampere per second. Then the inductance is 1 Henry. Right? So the final current, okay, the current will still start to increase. That one will start to reduce until finally it reaches a value. So the final current is determined by that V. There's a supply current. There's a supply EMF, sorry. Divided by R, the resistance of the coil. Right? Coil will any conductor will have resistance one. Usually we just neglect that. But have a resistance. We call resistance of the coil. Okay, so I'll let you digest. Give you some idea what we are going to start on next Wednesday. So you can go and review that. You can try some problem. So I'll stop here. Anything you want to ask, I'll answer you.
Yeah.
Okay, any question?
No, so far no, sir.
Okay, if not, we will stop here. Let you time to digest. And then we'll carry on next Wednesday. So have a good day.
Okay, thank you.
Have a good day.
Thank you.
Okay, bye-bye.
Bye.